Are you doing the honors? Or are you?
I'm asking you, but
Yeah, good. Yeah, Sam, do it.
Yes. Awesome. Okay, so we're excited to have our very own Melissa Zhang with us to talk about quantum invariants, ribbon concordance, Turaev genus, and contact topology.
Thank you, Sam. All right, thank you for sticking around for the last day and all of you online for joining us as well. This has been an awesome conference for me in that you'll see in my talk that a lot of the stuff that I've been working on with this crowd of people is related to the various talks that I've already been given. So this is a talk that's been cobbled together with like a bunch of different ideas and projects. And the point is that I kind of want to give you a sense of different ways that quantum invariants enter my world of topology. So in particular, we'll focus on ribbon concordance, derived genus, which you should really think of as like distance to alternating knots, and contact topology at the end if we have time, because that is also a very big cultural phenomenon in Georgia. So I want to just put that in there. Okay. This is joint work with a bunch of people. So Carmen Caprau, you might notice her name from punctoriality of Khovanov homology. She's at CFC Fresno. Nicolle Gonzalez, she works on a lot of algebraic combinatorics. So if you, well, yeah, I guess there are a bunch of different talks that she would be an expert in. Christine Lee is at University of South Alabama, and she, I should probably just not go through every single person here. But, she's an expert on the Jones polynomial and a lot of 3D geometry. Adam Lowrance is, I think I want to say an expert on maybe the stuff that Emma talked about, which I am not an expert on, so I can't really say so. And Radmila, who we've all met here. So let's go a little bit deeper. This slide is not really a roadmap as much as just, if you're thinking about what are these big topics related to, these are some of the ingredients that I'm going to use. So for instance, in ribbon concordance, this is quite related to Adam Levine's talk yesterday, where we're going to think about link homologies via these pictures of the Barnaton category, the most beautiful mathematics. But we're going to talk about this for SLN homologies. So if you've thought about Lucas Luart's programs for computing SLN homology, it's really using these pictures of what's called webs and foams. So we'll go into that a bit more, and then the actual content, which is ribbon concordance. For the Turaev genus part, we'll see again the ideas of Ruey Shan Lee and Shan Lee, which is kind of related to Sam's talk because you were talking about a bunch of different invariants, and you're measuring sort of unknotting procedures. Now, what I want to do here is actually measure distance between two knots that might not be the unknot. So in particular, more about like, if you think of the subclass of knots that are alternating and trying to measure how close are you to alternating, which depending on what invariant you care about could be like distance to thin knots, for example. So like a single delta gradient Khovanov homology. And then finally, I'll give you a sense of an ongoing project with these folks about thinking about braids in contact topology and using some of the stuff that Matt actually introduced to study transverse knots. Okay, so I don't expect to necessarily have to like go through all three of these. I'm going to skip some slides depending on questions that you ask. I want you to ask as many questions, and I'm sorry if you've already seen this. So first of all, let's first talk about what link homology is, and I'm saying this very generally. Link homology is coming from quantum invariants. The key here, at least in this talk, is that for each rank 2 Frobenius system, don't worry about that if that doesn't make sense. This algebraic structure of a Frobenius system, which is basically saying you have a ring and then an algebra over that ring, and it has these operations with some nice topological relationships. That gives you a TQFT, which is a topological quantum field theory, which basically just says I can associate to a circle a certain algebra or vector space, and then when I have a cobordism between circles, then I have a map between R modules. based on this algebra. So the four very basic cobordisms that we care about are drawn here. They correspond to these algebraic maps here. We really do like thinking about these as movies instead. So instead of drawing these pictures of the cobordisms that you can see in front of you, I'm going to translate instead to movies because we really live in four-dimensional space where one of the dimensions is actually time. And this allows us to think about embeddings in like four-dimensional space rather than just three. So as a movie, here the time is going up here. You're thinking about your maybe in like V4 and your radius dimension is going up. That's how the movie is going. And to remember these, you should really think there are four basic movie portions that you can glue into your movie. Birth of a circle, death of a circle, merging of two circles, and splitting of two circles, or splitting of one circle into two. Clearly, two of these are happier events, right? Birth of a circle is great, new life. Merging of a circle is also happy. The dual ones are kind of sadder. Like you don't want to break up and you don't want to die. We'll get back there. So let's talk about how we go from there to Khovanov homology and various different types. So for basic Khovanov homology, we've seen a bunch of times so far in this conference. You really have this idea of you take your diagram, you smooth it according to some rules, associate these vector spaces or algebras, come up with a complex, and then you get some chain complex. You can take a homology, and you can get Khovanov homology. In particular, in the framework that I showed you on the first slide, we are working with Z coefficient, so the ring is Z, and the module is this one. So the key to note here is just like we're using x squared equals 0. There are, of course, other flavors of Khovanov homology. So for instance, I could replace this x squared equals 0 with, well, I can put in some indeterminates with some variables and say, I'm going to mod out by some quadratic. So for each h and t value, you get something like this, or you could just say h and t are just variables. But of course, there's also information about the cobordisms, and we can use this to our advantage because as in the work of Barnaton, and also in Radmila's talk and also Khovanov's talk on the first day, instead of thinking about these as you take your cube of resolutions and you map this to the algebra and then you do your algebra there to do the homology, we can instead just work in the world of these surfaces and circles. Instead of using a chain complex and saying kernel mod image is homology, we can use a bilinear form on these surfaces with boundary. So we're going to take all of the resolutions and all the surfaces they've bound. For example, if I have a circle like this, it bounds a bunch of surfaces that look like this, infinitely many. You can have as much genus as you want. But this is too big, right? We actually want a circle to correspond to this like two-dimensional vector space or rank 2 module over Z. So you need a bilinear form to sort of put relationships on this set of surfaces. And let's see how this works. So this is exactly the same as the first slide. The relations, at least in Barnaton's category, you can, some of them look like this. So these are, I'm putting these here because they're relevant later. So for example, you could say that you have a sphere relation, which allows you to evaluate spheres with dots. How do you get dots? Well, you can take a tube like this and do this neck cutting relation, and that's how you end up with dots. And this is super useful because if you have too high genus, you can cut the genus down until you only have dots and caps and puffs. So yeah.
Maybe you're still explaining this, but I don't quite see the relationship. I don't see how you mod what it means to mod out by a linear form, or what equivalence relation versus bilinear form means. Maybe you're kidding.
No, I can explain it now. So
well, the thing down there looks like an equivalent relation.
Right, that looks like an equivalent. That
Not like
relations
really
equivalence
equivalent.
relation I'm fine with. Why would bilinear form?
relations. Related to like Khovanov's universal, or like related to what was in Khovanov's talking about this universal. See, have these closed surface evaluations, and somehow this course categories like you'll pose any relation which is a you set equal to 0 anything which is a radical of this value.
I see. So modding out is that kernel of the linear form?
That's right.
Oh, yes. Okay, maybe that should make more sense.
I see.
Yeah, so you can think of it as like, maybe even just with these two relations.
Yeah.
If you know just the basics of Khovanov homology, right? You have a circle and it bounds like, maybe take the one that bounces cup with no dot, take the one that, another one where it bounces cup with no dot. Glue them together, you get this sort of like, it's 0. So there's no differential that goes from like this one to that one. So that's like a very practical way to use these, right? On the other hand, if I had a dot, now 1 times x, x is like the dot. So 1 times x, if you glue them together, you get x back. So there is a, I shouldn't try to like recreate this on the spot, but this is the kind of way that we can use this. Okay, great. So now what about higher rank Frobenius systems? All I mean by this is I was modding out by these quadratics, and somehow if you want to think about SL3 homology, it's very much related to these algebras where I can mod out by a cubic. And for today's talk, I'm going to focus on modding out by just a very basic cubic, x cubed. Well, you can still have this TQFT picture, but this time you have to keep track of more information. And it turns out the way to do this, which maybe comes from work of like Cooperberg and then Khovanov and many other people, is that you have to replace your circles with these trivalent graphs, which we call webs. And then you have to replace the coordinate between circles with foams, because you could think about blowing a bunch of bubbles and squishing them all together. Each slice generically is a trivalent graph. You can always deform any sort of like 4-valent thing into like 2 trivalent things, right? So that's like the most generic thing. And then you can still add these dots. There's a lot of relations that are kind of complicated because you have so much more information, but you still have these sphere and net cutting relations. So for instance, if I have, this is my notation for I dots on a surface. I don't want to draw I of them, so I just labeled it with like a weight I. Well, it turns out the sphere relation says it's always 0, except if it's 1 less. Right, so 1 less than n. Same thing with net cutting. Now you just have this combinatorial sum of like all the different ways you can put dots on the cap and cup version. So this kind of harkens back to the previous picture. You can compare. And we'll only need these two to plus functoriality, which is very hard, but it has been done by people to show that these theories give obstructions to what we want to obstruct. So in fact, this is not just for SL3. As long as you have SLN homology where you mod out by x to the n, there is this topological description. So now let's take a break from that and go to the question we want to answer. First of all, if you take knots in S3 and you mod out by a relationship called concordance, you have an equivalence relation. Concordance just means it topologically, the coordinate looks like an ambulance, or it has 0 genus. I always feel like this is not the proper thing to try to teach somebody in 30 seconds. There's an equivalence relation. The cool thing is that this equivalence relation gives you a concordance group, so knots become a group. Now, the question is within each equivalence class, so if I have 2 knots that are actually concordant to each other, is there sort of one that's more complicated to get the other? And as we saw from Adam's talk yesterday, yes, this notion of ribbon concordance gives you this partial ordering on knots, and this was proven very recent. You should think of this as like, what is the hard thing to prove here? It's really saying like, if you have this one-sided relationship from this guy to this guy, and then also another one going backwards, they have to be the same knot. That's what it means to be a partial order. Okay, so how do I define this? A ribbon concordance from knot K0 to K1 is a concordance. So it's just a tube when you think about it, with only index 0 and 1 critical points. This is kind of hard to think about. Of course, there's like, Adam was saying like from and to are a little bit confusing. I have an opinion, which is that no matter what you choose your conventions to be, you should require a ribbon concordance to be a happy movie. So you can only have birds and meeting. You cannot have splitting and depths. So no, if you're doing your Morse function from 1 to 0, or if you're doing like, well, however you're counting it, just say that it has to be a happy movie and so this is a cartoon. If I'm going up like this, and this is ribbon, this is not. Okay. So here's some classical results. I guess Gordon was studying this, and he was really thinking about pi1 of the knot exterior. And if you have this ribbon concordance, then he says that you have this relationship between the two sides, right? So if this is less complicated, sorry, if this is more complicated than this one, then you can sort of inject the pi1 of the complement of the knot, this one, into the pi1 of the complement of the cobordism, or the concordance between them inside your, like, B4, well, just think of it as like R3 cross I or S3 cross I, right? Just inside this, specifically I'm thinking about B4 minus F. So I guess it's R3 cross I. And then you also have the surjection on the other one. So there's like an unbalancing, like one of them is sort of injecting, one of them is surjecting. But in February 2019, Zemke showed that you can use these homological type invariants to show that this sort of asymmetry is captured by the injection of homological invariant of one knot into the other. So now this is saying that K0 is not Floer theoretically speaking, smaller than K1. And a bunch of other papers followed, and you heard about that, one of them yesterday. Okay, so the critical lemma that allowed everybody to sort of jump on this train is called Van Some Wagon by Turaev, is that Zemke proved this topological lemma, which basically says if you take your happy movie and then you press the rewind button because you were born in the 90s and remember doing that, then you get this movie that's like forward and then backwards. And that movie can be manipulated using movie moves to get a cobordism that's equivalent to things that look like this, basically. Right, so you should really think of this as there's this, here's your first knot, this is the middle is like your second knot, and you go back to the first knot. And then every time you had the bursts, you sort of have a death at the end when you rewind. And then these behave well, and you can just do a net cutting relation here, evaluate the sphere that you get left over, and you use the TQFT to just study that cobordism. Okay, so here's the result for this first part. With this whole bunch of people, we showed that if you have one of the following quantum invariants, right? So things with webs and foams where you have this sphere and net cutting relation, well, you get the same result. So I put Levine-Zemke here because SL2 homology is Khovanov homology, and they were the first to show it for Khovanov homology. So if you have a ribbon concordance from K0 to K1, then your Khovanov homology for K0 embeds into this as a direct sum end. And you might first think, okay, is that a little bit stronger than injection? I mean, you see this in Levine-Zemke as well. You can come up with a partial, let me just write it down. Right, so here's the proof sketch. As I was saying, you just think about this topologically. The point is that the left inverse of your ribbon concordance is given by the SAT the rewind. So you actually just algebraically get an injection, invention. Okay, I know that was fast, but I want to emphasize that the point of this project is that if you have these topological descriptions, you can prove all of these things. Any questions before I move on to the next one?
Well, the hard part is the bookkeeping.
Yes, it's not that bad. I think it's not that bad. There's a lot of dots, but it's like 1 or 2 pages. All right, so part 2. Actually, the same paper. Now we want to talk about quantum invariants and measures of distance between them. Let's first talk about the lead spectral sequence, because this is going to show up as a measure in Lagrange-Champy-Darwin. So recall that I defined Khovanov homology correspond to the Frobenius system, where you take, let's say, z adjoint x and mod out by x squared. Unsu Lee defined Lie homology as a perturbation of Khovanov homology. All that means is that I'm changing my quadratic a little bit, and now it has 2 distinct roots. Rasmussen saw this and said, well, I know that in Heegaard Floer homology, we can define this thing called the tau invariant by measuring this standard piece of each knot homology. So somehow this standard piece is like characteristic of the concordance class, whereas the torsion part is more about the specific knot itself. And the same thing happens here. The lead homology itself is just this standard concordance invariant. It's this like free module. And the only information that it holds is that it has some grading. And so Rasmussen's invariant is sort of like the grading of this lead homology. But you can also think about the spectral sequence itself as an invariant of your knot. So one number you can pull out of a spectral sequence is what page has your spectral sequence collapsed? So when does it eventually reach lead homology? Right, it could be page 2 or something, right? So then it would immediately collapse. But it could be like page 5, and that would be like there's a little bit more distance between Khovanov homology and lead homology. Okay, so if you're in the same concordance class, right? K1 and K2, K0 and K1 are in the same concordance class. Certainly their lead homology is just going to look the same. But how far are they? That could be measured by how much you have to cut off, right, to get to lead homology. So, yeah, you know what I just said. So there's this is a separate section, so we won't talk about that. Okay, but similarly, there is a Barton spectral sequence. The idea is that you can't really do lead homology over characteristic 2. Like Radmila 2 invariance gets a little bit, you can't divide by 2. So that's a problem. But there's Barton homology, which is somewhat equivalent, well, twist equivalent to lead homology when you're not over characteristic 2. But I think of it as more general. So this is a whole page of distance measurements. If you know about the unknotting number, which is right here, well, what you want to say that the unknotting number is how many crossings do I have to change to get to the unknot? There's no reason for you to only study the unknot. You can say, my favorite knot is a trefoil, and I want to see how many crossings I need to use to get to the trefoil. But there's no reason for you to pick a single knot. You can say, I have a family of knots. What is the distance between some random knot and any number of this family, and take the minimum? Right, so this notion of distance between knots, I'm going to call Gordian distance. It's just the minimum number of crossing changes you need to do to get to whatever you're trying to get to. So Kouchi defined the alternation number as the distance between a knot and any alternating knot, well, the minimum. You can also similarly, now that we know about homological invariants in knots. So if you know about these, this is like you're supported on like one delta gradient. So you're like homology is defined by a polynomial. Like there's not really extra information from Khovanov homology or not from homology. Okay, it turns out that all alternating knots are Khovanov thin. So we have this relationship between these two numbers. There's another different measurement of distance to alternating knots. And this is called the Turaev genus, which I'm writing as G sub T. And the way that I like to describe it is if you just actually think about taking each diagram that you have for a knot, and you think about the different ways that you can change the crossings, so smooth out the crossings. But when you smooth out the crossings, you actually build a surface, right? So it's a cobordism between the all zero resolution. So you could draw like all zero resolution in Khovanov homology. And then you take some path through the cube and you record that entire cobordism. So that's actually a smooth two manifold, right? So you go from all zero to all one. And then now you have a bunch of circles at the all zero resolution and a bunch of circles in the all one, and you just cap them off. And that is some closed surface, and you want to know the genus. So if you take over the set of all the diagrams for knot, you do this operation, you look at the genus of the closed surface, that is the Turaev genus. Well, sorry, the minimum of that is the Turaev genus. Yeah, so for example, in this picture, I have the unknot. The Turaev genus is 0. Yeah, 0. Because if I take this unnecessarily complicated diagram, I see that I can go from two circles to one circle, and then I cap off the bottom and top, and then I get a sphere. You could actually sit down and try to compute the genus of a surface based on, how many, what's going on with all my resolutions. And this is just for you to like peruse later if you're interested in those details. Now, Turaev showed that K is alternating if and only if the Turaev genus is 0. You could probably try to work out on your own, like when you have D is an alternating diagram, can you try to show or get a sense of why the Turaev genus is going to be 0? Okay, so here are some important remarks. Alternation number, which I guess I might have written as D alt earlier, there are knots that have wildly different alternation number and Turaev genus. So somehow these are two very different distance measurements. And I'm not really sure what difference these two are capturing. Okay. Are there any questions so far before we move on? So now I'm going to review, I guess, stuff about Holly-Shafi and Alan-Shafi-Dowland's approach to a knotting number. And I'm going to go through this pretty quickly because you've somewhat seen it once, and it's really important to kind of sit down and work out the proof yourself to really understand what's going on. Let's think about Barnaton homology, but now with this extra variable H. If you have, if you take this Barnaton homology, there's an action of H, and you can define the order of a homology class as the minimum number of H's you need to kill the class. So this is just some measurement. Holly-Shafi defines this max frac U as a maximum over all of the torsion classes alpha that that you need to kill off. So like after you've multiplied your whole homology by Hn times, you're only left with a free part, basically what you're saying. And you can see how this is kind of related to the spectral sequence, because what you're doing with the spectral sequence is also just sort of turning the page and considering longer and longer differentials until you end up with a linear homology, which is free. So Caprau shows that this is a lower bound of the nodding number. And this is actually a better bound than just using Rasmussen's there. So Alishan and Dowland do this for Lee homology, and there's sort of like instead of each torsion, it's kind of X torsion, which is kind of related directly using formula to this T torsion. The reason why I'm showing you both of these is because, of course, there's this problem with characteristic 2 for Lee homology. And the point is that there is the same sort of phenomenon going on, but I'm going to state all the theorems in terms of both. But you can focus on one of them, whichever one's your favorite. Okay, so this is a sketch of the proof, which I don't feel like I'm the best person to be telling you about in this room. So I made it really small. But if you can remember from, I think it was Adam's slide yesterday, there's this picture where you basically say, I'm going to define some chain maps, right? And then this is the proof that you should work through by yourself because you totally can do it, given that you know some homological algebra. And it's really cool. And then you can prove it, but the star is right here. So move on. Okay. So here's an aside, which is like, if you really want to know the relationship between torsion order and spectral sequence, there is a relationship. So for Lee homology, you can kind of figure it out yourself if you know both of the theories. Okay, let's talk about the results. So it turns out the page that on which your spectral sequence collapses is also going to be a lower bound for your D thin, you know, with this operation applied to it, which of course is also D thin itself is less than or equal to the alternation number of K. So you have both of these bounds. And you have this for both the Barnaton and Lee theorems. Now, the other distance measurement I talked about was Turaev genus, and you have a similar, more simple looking page of collapse of Lee's spectral sequence bound on Turaev genus. So hopefully this is somewhat believable. Let's talk about a sketch of the proof. This is too much to fit on one slide because I don't have like a board that slides up. So I have to sort of condense it to here's just the proof content, which is enough for talk, and here's the proof idea. So there's work of other people, Kaufman and Schultz, which says that the width of Khovanov homology, right? So this is what D thin is based on, is going to be actually related to the Turaev genus using this formula. So you basically just think about, okay, I'm turning the spectral sequence pages. My differentials are getting longer and longer and longer. And if I have a really thin Khovanov homology, eventually my differentials just run off the page, right? There's like only zeros. And that's kind of how you get this result. Okay, and then the same holds for, I mean, use this for Turaev genus and this for just. There are some applications for particular knots in our paper, which I won't go over now, but this is the end of the second section. Are there any questions? Okay. Third section. Okay. This is going to be a little bit rougher because I don't think very many people have talked about this material in this conference, but feel free to ask me questions. Yeah. So the third part, I wanted to talk about how you can use quantum invariants, go through braids, and go to contact topology. So maybe the first thing you should think about is that the braid group on n strands is really the same as the mapping class group of you have just a disk and then you have n punctures, because as you move the punctures around, every time you finish one braid, the punctures are back, maybe shuffled, but the path that they took is a braid. So Bennett can prove the transverse Markov theorem, which says that any transverse knot can be represented as a braid. I'm not going to define what a transverse knot is, but you should think of this as if you have a contact structure, think about the rotationally symmetric one, and then draw your braid around the z-axis. Okay. Now, if I have a braid, I can talk about this thing called the fractional Dane twist coefficient. This is a more general thing. You're sort of measuring how much your braid is as a diffeomorphism wrapping around some boundary component of the surface. So in this case, we just have one boundary component, boundary of the disk. And for a braid, the fractional Dane twist coefficient is the fractional Dane twist coefficient of this boundary component that we're going around. So if you want a very concrete definition, you can look at this thing called the Doudna order, where basically you're able to compare any braid between fold twists. I'm just realizing this kind of harkens back to Peter Feller's talk, right? You're kind of like squeezing it between these torus braids, right? You close it up with the torus. And this is like an actual ordering, a total order on your braids, and you can always say like, well, it kind of twists more than m full twist, but it twists less than m+1 full twist. And that number is your fractional Dane twist coefficient if you homogenize. Okay. Now, so if you combine work of Khovanov and Oshvat Sabo, this is just a sense of like, why do we care about these quantities? If you're a contact topologist, you might say, well, suppose I have a contact structure, and there's this way of thinking about contact structures where you actually start thinking about a surface and a diffeomorphism on that surface. And so now you can study this diffeomorphism. Well, it turns out the fractional Dane twist coefficient being at least 1 tells you something about the contact structure itself. Again, I'm not the expert in this room. So if you want details, I think there's someone better, although you're welcome to ask me. So I'm going to think about these transverse knots in a rotationally symmetric standard contact structure on S3. There's this interesting theorem of Khovanov that says, well, if I have a 3 braid, a very special case of braids, then if every braid representative of the braid closure is right veering, which is another sort of contact geometric quantity property, then there's this invariant coming from Heegaard Floer homology that has to be non-zero. So for the purposes of this talk, just think like there's some invariant, and it kind of is capturing this contact geometric property. If you go to n braids, well, it turns out right veering is not the right thing to think about anymore. You actually want to think about the fractional Dane twist coefficient. So that's another reason why it comes up. Again, this invariant is non-zero when this is true. So these are reasons to think about the fractional Dane twist coefficient. Now in Khovanov homology, there's this transverse non-invariant called Platonovskaya's invariant. It's basically a class. It's a homology class, and it might be 0. You compute it from taking a braid representative of a transverse knot, and then just checking what this class is. Like usually we would say, is it non-zero or is it 0? And that's the invariant. Yeah.
So can I ask, how does the set of braid veering knots compare with the set of fractional Dane twist number 1 knots? Is one of them the same?
If your fractional Dane twist coefficient is 1, you have to be right here.
Bigger than your 1?
Yeah, so right veering is like, I'm standing at the boundary.
But if you make the back twist, it's not, it's right, you have right Dane twist, it's right here.
Okay. So it is the same if your fractional Dane twist is bigger than or equal to 1, then you are great there, but not 100%.
Yes.
Okay.
Yeah. Yeah, I mean, you should think of it as this theorem is stronger for 3 braids, right? And like weaker for higher.
Yeah, interesting. Okay.
Yeah, so there's this homology class, and if you want to see what it is, here's a representative. One big problem is like psi is supposed to be the Khovanov analog to this theta from Floer homology, but we don't actually know how useful it is. That hasn't stopped me from using it and thinking about it, right? Because even if whether it survives or dies isn't useful, you can still think like, oh, how long does it survive in a spectral sequence and things like that, right? It's still sort of worth thinking about this and how to maybe bring it to other versions of Khovanov homology. So the bigger question that I want you to really focus on is what geometric information does Khovanov homology have? It's possible that the reason why this invariant isn't useful for transverse knots is because Khovanov homology just really likes thinking about things in 4-ball, smoothly, not geometric. But I kind of want to know that that's true. So in order to study this, I'm actually going to go back to stuff from Matt's talk, sort of, and as an aside, talk about stability in Khovanov homology. So in Matt's talk, there was this thing called the Jones-Wenzel symmetrizer. There were also these Kirby colors, which were these limits of these complexes of tangles that get more and more complicated. The Jones-Wenzel symmetrizer is actually the limit of a bunch of full twists. And you could imagine how you could get maps from, say, you have 2 full twists. Somewhere, right, if you can think about what that map would be to go to 1 fewer full twist. Similarly, if you have negative full twists, it's kind of like a dual version. I have 2 copies of this. Now, Diana Hubbard and Christine Lee showed that if you have a knot that is given by the closure of a braid, and the braid is a 3 braid, so once again, it's like more special case of the 3 braid, and your fractional day twist coefficient is greater than 1, then you know that Khovanov's invariant is non-zero. So this is kind of saying like, okay, it's a 3 braid and it twists enough, then contact geometrically, it's sort of like, I don't know if you want to say what you want, but you know, it's sort of like interesting, more restrictive. Okay, so then the question is, well, this guy was able to prove this thing about 3 braids, and then also a second part of the theorem for n braids, which is slightly different. So what's going to happen in the Khovanov case when we actually extend to higher index braids? So now we're already using fractional Dane twist coefficient here. How would you think about generalizing that? Well, maybe it just has to be greater than some other number, or maybe it's the same condition. We don't know.
Not equal to 0 there. Second part of the question. See if k not equal to 0 if dt is.
I think yours is exactly.
You wrote equal 0. See
Oh,
if
no.
k equals 0. The second line of the question. Third line.
Oh, sorry, yes, the third line. Yes, thank you. Yeah, so you think about it, if you have a stabilized knot and everything just like breaks, that's not the interesting case for me. Okay, so you want to ask this question for all braids. But since we're doing fractional Dane twist coefficient, and we know that all the braids are like somewhere between the standard torus braids, right? Let's actually look at just the worst case scenario. The worst case scenario would be these things called twisted torus braids, right? So if I want to have some number of full twists, like a fractional Dane twist coefficient of m, I know I should probably have something like m full twist at the top. But the rest of the braid can be as negative as I want. That's allegedly what I'm conjecturing to happen. So I'm going to take like n-1 of the strands and twist them negatively, like a lot. And what do I mean by a lot? I mean take the limit. So I'm going to take this full twist with m full twist, and then connect onto that tangle just infinitely many negative twists and just see what happens there. And this is something you can do with quantum invariants, right? Because they have these, you have tangles and you can actually just glue them together and study the complex. Oh, that was sudden. I think I'm missing a slide. So I guess I should say that we at least know that you can recognize this limit of Khovanov's invariant inside this horrendous infinite complex. This is pretty horrible because, as Eugene said yesterday, this tangle, which is like a cut open torus braid, its homology is not very well understood. So a lot of this project is sort of saying you have this infinite complex going in the negative direction, and you want to tensor it with some finite complex that we don't quite understand. But perhaps there's enough information there, because this is so symmetric, that we can glean what's going on with a particular homology class, which is at like 0, 0. So there's a lot of combinatorics studying this, and we think that with methods that we've come up with here, whatever we can do with the complex, it'll be useful to other people. And then for us, doing the homological algebra, this part is more about the compact geometry. Okay, so that's all I have to say. Thank you very much. These are the lovely ladies that I'm working with on this third part of the project. And you can try to guess which one's me. Thank you.
Questions from Melissa?
Yeah, could you describe this order again? Yeah, that helps you define the rational things. Yeah.
The order, the doorknob.
Yeah, this order. Or like what kind of invariants go into this definition? Like is it?
Yeah, so I can give you like a rough idea and just so that I don't remember the detail. Basically, you want to factor like a full twist to some power to the beginning of your braid. Right, and then there's sort of, you know what, I should get back to you on that.
Oh, okay.
You should, but I don't remember what the operations are to get sort of this twist and then stuff.
Okay, well, I just wasn't sure what the order is. But we can talk about it.
Yeah, I think if I just go to the Wikipedia page on the order, then yeah, we can talk about that.
I have a question. So in the Khovanov invariant, you said it's open whether it's useful or not.
Yeah.
But then doesn't the 3 braid result that it's non-zero if whatever exact hypotheses, doesn't that tell you it's useful, or maybe there's no known example where it's 0? I mean, does it allow you to distinguish something about 3 braids?
I mean that its life or death might be just determinable by like self-linking.
Oh, so I see.
So like you can just use older invariants that are perhaps easier to compute and not go through homology and just think about the same thing.
Whereas the corresponding Heegaard Floer one is known to be.
Yeah, so it's like it distinguishes better than like classical invariants.
Thank you once again.
Yes.
Yeah, the next stop is at 11.